Okay, so today's lesson is lesson 2 in our probability unit based on dependency in probability and probability trees. So we're going to be talking about compound events today. So compound events is when you have a scenario which deals with 2 or more separate events. Now those events can either be independent or dependent events. Independent events is when the outcome of one event does not affect the probability of the outcomes of the other event. So basically the two events don't talk to each other. The second event has no idea what happened in the first event. And when I say first and second, they don't necessarily have to go in an order. So just kind of keep that in mind. Dependent events is when, based on what happens in event A, that's going to change the probabilities of event B. So event B relies on whatever happened in event A. So I'm going to give you a list of 4 different compound events, and I want you to pause the video and think about, are these independent or are these dependent events? So first one is rolling 2 dice, drawing 2 cards, rolling a dice, then drawing a card, or finishing first place in a round robin and then winning the tournament. So if you're not a sports person, round robin are the games that are pre-set up where you just play everyone. And then winning the tournament would be obviously winning the playoffs. Okay, so hopefully you thought about where they went, paused if you needed to. I'm going to reveal the results. So rolling 2 dice are independent events. The dice don't talk to each other. If you roll a 3 on the one dice, probability of rolling a 3 on the next dice is still 1 out of 6. Even if I roll a 3 7 times in a row, the probability that I roll a 3 on that 8th time is still 1 out of 6. The probability of all of those things happening together is really low, but the probability of each individual 3 is 1 out of 6. Rolling a dice and then drawing a card, very similar, right? The dice doesn't talk to the cards. The cards are just still a full deck of cards. Nothing's changed with those deck of cards based on what happened with the dice roll. Whereas drawing 2 cards, after I've drawn the first card or dealt the first card, there's now less cards in the deck. So the probabilities have changed based on which card came out. So if I want to draw an ace on that second card, well, that probability is going to be dependent on if I drew an ace the first card or not, right? Are there 3 aces in the deck or are there 4 aces in the deck now? That matters. Next one, placing first in round robin, then winning a tournament, that's also dependent. If you place first in a round robin, you end up getting a better seed for the playoffs and you end up having easier games. So let's say it's a 4-person or 4-team playoff, then first place plays against the last team to make it through to the playoffs, the 4th place team. So it's an easier semifinal. Okay, moving on, looking at some examples. So this first one is in the medical field. So it is estimated that 12% of the population have a particular genetic defect. The test for this particular genetic defect is accurate 97% of the time. How many people out of a study of 1,000 people would you estimate to have the defect but think they do not have the defect? Okay, so now we got to ask ourselves the question, what are the events that are actually occurring? What are the events that I want to use for the calculations? So what are the results of each particular event? And how are they going to be combined together? Are they dependent or independent events? So first, let's just define our events. So the first event is the person has to have the genetic defect. The probability that they have it and think they don't, that means they have to have it, okay? The second piece then is them thinking they don't have it. In order for them to think they don't have it, they would have had to have a test, and the test would have been a false negative. So the test would have come back negative, but in fact, they do have it. It should have come back positive, but it was wrong, okay? And what we want is we want both of these things to occur, right? And by want, I mean like that's what the question's asking. I don't want this to happen to anybody. But we want both of them. So we want this to be like an and situation, right? This is and. That's really important. If we think back to the unit on counting techniques, and versus or, that's going to come into play a lot in this unit as well. So make sure you really know those counting techniques. Another way of thinking about this is just imagining it as a Venn diagram, right? If we have the first set of people who have the genetic defect, so D, and then we have another set of people who got tests that were false negative, We want to find all the people that are in this section. Well, what did we call that section? We called that section the intersection, right? Where both of those circles, both of those properties occurred. Okay, so if we called it the intersection, we can start writing our probability statement. So our probability statement is equal to the intersection of D and F. And that's going to be multiplying those two probabilities together, again, because it's an AND situation. AND is multiply. So if I want to continue working with this, we're going to say probability of the intersection. Probability of having the defect is 12%, so just convert to a decimal or a fraction, times probability of having the false negative test. That's actually not given to us in the question, though. What is given to us, though, is the probability that they have an accurate test. So that's the complement of getting a false negative. I could have defined the event differently in saying they had an accurate test as well, and then I just wouldn't have to write the complement like that, and that would have been fine. So continuing on, I can sub in that value. 0.12 times 1 minus 0.97. And when I calculate that all up, I end up getting 0.0036. Okay, then I reread the question. Have I actually answered the question? Well, the question was the last sentence. Oh, it says how many people? We have not done that. We haven't finalized the question. So we need to make sure we do that. So we want to know the number of people that are in that intersection. Well, that's going to be the number of people in our study, so the number in our universal set, times the probability that they had both of those things occur. So number of people in the intersection have the defect and had a false negative test is going to equal the total number of people times 0.0036. And that ends up equaling 3.6 people. So therefore, oops. There are approximately 4 people with the defect who think they don't have it. And obviously this is really important going down the road in that person's kind of medical experiences, not realizing you're having something and feeling confident that you don't have it. You might end up taking certain drugs to help you with other medical issues, and then there might be some complications or things like that. So we're always trying to kind of minimize these occurrences. This also comes into play in crime. Oftentimes, medical experts come on the stand and they will, testify to something being true, when in reality, there's a probability that those things could be false negatives. And I might post a video if I can find one of some very famous law cases that had that come into play as well. Okay, moving on to the next question. Oh, actually, I want to talk about, this is independent, because whether or not they have the genetic defect or not, this 97% is always 97%. This accuracy of the test doesn't know whether the person has the defect or not, okay? It doesn't change. It's always 97% accurate. Okay, example 2. So you're playing a game. The first part is to roll 1 dice. If you roll an even number, you move on to the next part, which is drawing a card. If you get a red, you win. If you roll an odd number, you flip a coin. If you get heads, you win. What is the probability that you win the game? Okay, so this is like the most exciting game ever, right? We get to roll dice, draw cards, flip coins. Woohoo! All right, so let's kind of look at this one in terms of a tree diagram. Since there's 3 different pieces going on, sometimes the more complex things are, it's actually easier to draw it out. We could do this algebraically as well, but let's explore this method. So we're gonna look at rolling a die, drawing a card, flipping a coin. Tree diagram is the same as any other tree diagram, except now we're going to include probability on it. But we're going to look at the different outcomes of rolling a die. Now, if I looked at every single outcome, I'd have 6 branches here. 1, 2, 3, 4, 5, or 6 on my dice. But I don't actually care what number's on the dice. All I care about is if it's even or odd. So those are the two outcomes I'm going to list. Those are my events, right? The outcomes for even are 2, 4, and 6. The outcome for odd are 1, 3, and 5. But the events are even and odd. So to get to drawing a card, I need to get an even. To get to flipping a coin, I need to get an odd. To make this probability tree, we put the probability on each branch. It's 50% probability you get an even, 50% probability you get an odd. For drawing a card, the important part in the question was getting red or not. So that means we can either get a red card or the other color cards are black. Again, I'm not listing 52 different branches of this tree diagram. Just the two events that are important. What's the probability that I get a red card? Well, it's a half. It didn't matter what happened before with the dice. The cards, they're not affected by that. Black, half. Flipping a coin. I can get heads or I can get tails. Again, half, half. We're getting pretty exciting here with our math. Lots of halves. Okay, so when you're drawing a probability tree diagram, like anything that you're doing, you should always use a ruler, but I don't think I have that function on here right now. What we want to do, though, is we want to look, what's the probability that we win? Okay, well, how can we win? Well, if I go even, then I need to get red to win. So I need to go through this set of branches. I need to do this and this. Okay? The other option is that I go through the odd set and I get heads. So I go that way. Again, and. Okay? And then between the orange and purple, that's an or situation. Okay, so now we got lots of stuff going on. So let's find the probability of the yellow branch. So yellow branch is and, so it's 1/2 times 1/2, it's 1/4. Purple branch, again, super tough math. To get odd, 1/2. And to get heads, 1/2. Multiply those together, bada bing, bada boom, we get 1/4. Okay, now this or business, what does that mean? That means that we're going to add those two pieces together. So the overall probability that I win this super exciting game is going to be 1/4 plus 1/4, which is 1/2. So it's 50% probability that I win. Super exciting math game. Okay, let's try another one. Again, we're going to do a probability tree. This time we're going to talk about soccer. So probability of TFC, soccer team, winning the first leg of an aggregate match away is 40%. If they come home with the advantage, meaning they won that first game, then they have a 70% chance of winning overall. If they had lost in the away game, then they only have a 50% chance of winning overall. What is the probability that they win overall? Okay, so you notice I was saying overall instead of aggregate. If you're not a soccer aficionado, then you've probably kind of never heard of this philosophy. It's very unique to soccer. But what they do is they actually play 2 matches, 1 match away and 1 match at home. And whichever team has the higher total score wins on aggregate, what they call it. So they win that particular series. So it's not really like a best of 7 or a best of 5 like other sports do. They just play 2 and they take the total scores for each team. So if TFC had won, then they're coming home feeling a little more confident. They can play a little more defensively, so they have a higher chance of winning overall. But if they lost, then they might need to be a little more aggressive. And so there's more chance of them kind of giving up more goals and then not winning. So the things that need to occur is we first need to look at the away match, and then we need to look at them winning overall. I don't actually need to look at them winning that second game at home. There's no information kind of about that. All I really care about is the total score, them winning on aggregate. Okay, so the away match, they can win or they can lose. If they win that game, or the probability of winning that game is 40%. If they have 40% chance of winning, they have to have a 60% chance of losing. That totals to 100%. Any set of branches that go to a node are for one particular occurrence, and so the total events need to occur for 100%, or need to total 100%. So then going from the win to winning on aggregate, well, again, they can win on aggregate or they can lose. So this title isn't actually very good. It shouldn't say winning on aggregate. It should just say aggregate. Them winning on aggregate. Okay, well, what's probably they win on aggregate? Well, it talks about that a couple times, right? It says if they come home with the advantage, well, that's if they won this game. Okay, so they did that. Then they have a 70% chance. Great. And then this comes to a node. This is one particular piece to the puzzle. So then this has to equal 30%. Okay. If they lost, they still play the second game. They're still going to try and win on aggregate. That could still happen, but they could also lose on aggregate. So what's the probability they win on aggregate after they lose? So if they had lost, they only have a 50% chance. So this is going to be 50. This piece down here also has to be 50 then to total to 100. So then, what's the probability that they win overall? Well, they have to go through this set of branch, again with an and. Or they have to go through this set of branches again with an and. And again, I said that was an or situation. Okay. So winning and then winning would be 40 times 70. And then losing and then winning is 60 times 50. Again, decimal, sorry. And then we need to add those two pieces together to get the overall probability of winning. So the overall probability of winning, if I whip out my little calculator here, 0.4 times 0.7 plus 0.6 times 0.5 ends up giving us 58%. So they are sitting with a 58% chance of winning on aggregate. And that would be my therefore statement. Okay, if we want to take a look at this exact same question algebraically then, because like this isn't really good communication here, right? Like I'm not putting a lot of detail there, mostly just basing it on the diagram. But if we wanted to put it all in algebraic form, this is what it would look like. So it would be probability they win overall, would be probability they won the first game, times the probability that they won on aggregate after winning, plus probability that they lost the first game, times the probability they win on aggregate after losing. Look at all the detail that has to go in here, right? Like, it's not just times probability of them winning on aggregate. I need to say that it's probability of them winning on aggregate after winning, because that's going to be different than this. These two are not the same. That's what makes this dependent events. The fact that second piece has changed based on what happened here. Okay, and then again, we'd continue this down, and then we'd put in our numbers. So one first game was 40, one afterwards was 70, plus lost first game was 60, and then winning after that was 50, and then we'd get the same answer going forward that way. Okay, but because there's so much written in here, we need to kind of think of a more concise way to write that, because ain't nobody want to write that every time. So we're going to use this particular notation. So I want to draw your attention to right here, right now. We'll kind of talk about the overall slide in a second. What does that line mean? Okay, well, if we think back to like function notation for domain and range and things like that, you may have seen the vertical line, meaning such that, like such that x is an element of R, or such that x has to be greater than 5, or whatever. In this case, it means such that A has occurred. Or you may hear, instead of such that, you may hear given that. So given that A has occurred. Either way is a fine way to read that, okay? But basically it's saying that like after A, what's the probability that B happens, okay? That's the only difference between these two formulas. So again, they're both ands, because we're looking at two events and having both things happen because they're intersections. And so that's why we're multiplying. Okay, if we want to build it more, and there's more than one way to get these ands, then there could be some ors as well, and we could be adding on top of that. But if we have two things occurring together and it's and, there's definitely a multiply involved. The only difference between independent and dependent, with independent events, this probability of B is set from the get-go, and it's one number, and it doesn't change. This probability over here depends on whatever A has. So you can't just say probability of B. You have to say probability given that A, right? Probability that they won given that they lost. Probability that they won the playoffs given that they won the round robin. That kind of idea. Okay, so this is a really important summary slide that you might want to pause and write down. Okay, and where it is a little bit of a simple one in terms of the calculation, but we're going to really focus on communication here. So what is the probability of drawing a diamond, then a red card? First thing we're going to do is we're going to define our events. So event D, the first thing that we want is to draw a diamond. Second thing we're going to look at is to draw a red card. And we want both of those to occur. So this is an and situation. Okay, so since it's an and, we're going to be using the product rule. There's only one way for it to occur. Because I've put this then, it can't change the order of which it can occur. Okay, this would be a little bit more of a complicated question if I didn't put that then there. If I just said pick a diamond and a red card, there'd be a little bit more going on. So if you want to challenge yourself, you can try that question a little bit later. So now we need to think of what the formula would look like. If I wrote this down as an intersection question, people would think I'm drawing a red diamond, just drawing one card. I want to make it a little bit more clear that we're actually drawing two cards in this case. So I'm going to say probability of a diamond, then a red card. Just to kind of show that one thing occurs, then the next thing occurs. So that's going to be the probability of me getting a diamond. And then it was an and situation, so it's going to be a multiply. And then I can't just write probability of red, though. Because if I did that, it would be 1/2. Because there's half the cards in the deck that are red to start with. But there's not half the cards in the deck that are red that are left. Because I've picked out a diamond. So this doesn't work anymore. So now we have to communicate that we've picked out a diamond already. So this is going to be probability of red, given that the diamond has already occurred. Okay, so again, this means probability of red after, or given that, or such that the diamond is gone. Okay, so now if we convert that to cardinality statements, number of diamonds over number of cards in the deck, number in my sample space, cardinality of my sample space, okay, times cardinality of this is going to be, again, the exact same thing that's in the brackets, number of red, given that we've already pulled out a diamond. Now, if we've already pulled out a diamond, that means I no longer have the 52 in my NS. So I'm going to call this reduced sample space. So NRSS. That's reduced sample space. And basically what that means is just what's left. After you've done the first particular piece of the experiment, after you've drawn the first card, what's left? In this case, in the deck. How many cards are left? 51 cards are left. Okay. So now we're just summing our numbers. Number of diamonds in the deck is 13. Number of total cards is 52. Number of red cards that are left, well, one of the reds are gone. Diamonds are all red. So there was 26, now there's 25. Out of how many cards are left in the deck? 51. Okay. Then we go through and we punch that in our calculators and we find the answer to that one. So we go 13 over, we're going to use our fraction button on our calculators. I don't have a regular calculator and there's no fraction button on this, so I have to start it one more time. No, I'm just going to leave it up and I'm going to find the calculator and then I'm going to come back to it. Calculator, calculator, calculator. So we're going to use our fraction buttons on our calculators. We could also do some reducing techniques here, but we'll just kind of save ourselves a little bit of time and just punch it in our calculator. Using the fraction button on your calculator allows you to actually get a fractional answer. And again, remember, fractions don't involve any rounding. So fractions are more accurate than decimals. That's why we prefer fractions. So that's the exact value. But again, our brains work a little bit better in terms of percentages. So then we do the division on our calculators, and we end up finding out that that is 12%. Probability of drawing a diamond, then a red card. Or drawing a red card after getting a diamond. Okay, so in summary then, again, the top part of this is the exact same as what we've done before, but on the bottom it just shows you that kind of reminder that the and or situation, times and adding, still holds for probability just like in counting techniques. Okay, so if you only copy down one thing from this note, but hopefully you're copying down more, this slide is the summary of this lesson.